This is a LabVIEW Beginner Lesson Series. The focus is creating a heart rate monitor. Today we'll continue on the simple heart rate monitor and we'll make the filter. This is lesson 2-2, filtering the signal. We'll be filtering the frequencies that's outside of the range of a human pulse, because that will probably just be noise, and there will be noise. We will pad the signal in such a way that gives a better filtering result. And at the end, we'll add a function that can remove the start of the filtering signal. We'll start by copying this one. At this point, again, you don't need to, but it is good to do just so you see the progress. You could also save it by GitHub, etc. But let's just do this. Continue, and then let's name it. And this lesson is called Filtering the Signal. Filtering the signal. What we want now is to filter this raw data so we don't get noise. If you see now, we will have a lot of these jagged edges. Oh, we have to set from last time. With all of these jagged edges, we see this noise. I'm not doing really anything. Now I'm covering it. But all around, we see this noise, and this is what we want to remove. We'll just stop it. And we'll just expand this a little bit so we have room to operate. We'll just leave this one here too. So I press hold Control to move it this way. We'll start by picking up a filter. We'll go to signal processing and then filters, and here we'll select a Butterworth filter. There's a lot of other filters too, but we're not focusing on the different types of filter. We just want a filter that works. We choose a bandpass filter as we want to filter out lower and higher frequencies than that we don't want to use, because your heart rate will not go under 40 beats per minute and probably not go above 200. We'll set the limits later, but the point is we want to set like a lower limit and a higher limit, which is our band, and that's why we choose a bandpass filter. Here is where our signal will go in, and as last time, we will need to unbundle this, or as it's called with waveforms, we need to get the waveform. This also needs the frequency in, but we don't get the frequency out here. We get the time between the samples in seconds, which is not frequencies. Frequency is 1 over the time between seconds. So what we need to do is to put out a block which turns the time into 1 over it, so it becomes a frequency. We then need to decide the cutoffs. So this is the higher cutoff, and this will be the lower cutoff. So to figure out what we want to put in here, we need to calculate. So the person will probably be standing still, sitting still, as this will be a sensitive thing. So the heart rate won't be too much. It will probably be at maximum 120, maybe 140. So let's just say 180 to have the limit a little bit over what we potentially will get. This gives us a nice number 3. So let's clear it, and let's take 20 divided by 60, which is 0.333. To make it easier, we'll just say 0.3. This is a nice range, and then we'll just add about 20 beats per second. We don't need it to be exact here, because we're going a lot lower than we would. We just need ballpark numbers here. We don't want it to be too close, because then it could filter out good signals, the heart rate. And we don't want it to be too wide, because then we will let in a lot more noise. We can now push this back into the signal, and we'll have our filtering. We'll go to waveform, and then build waveform. Put this here. Put this in there. And create a new one. We'll just copy this one. So let's make this one a little bit bigger. Put it there. And then just write filtered data. Okay. Then to find it on the block diagram, you can just double click it and you'll get directly to it. And there you go. Here we have our little filter. And there we go. Now we have it inside a VI. Now we can just place it like this, and it looks much better. Let's save this VI. Let's select here, and we have filter waveform. Let's just copy here, filter waveform. And we'll edit this icon. And this is filter waveform. And now we have our VI. But as you saw, there was this little thing at the start. We want to remove this. And to do it, we can just set up a function which can remove part of the signal. So we'll do that here. We'll do that after we have filtered the signal. You just move this here and we'll write here, filter the signal. So we'll need this one and this one again because we want to unbundle it and then remove parts of the data. And here, this function is very similar to the function we have here. So we can actually compare these two. So what we did here, we removed the end of the signal, like the oldest signal is what we removed here. And that's also what we want to do here because this loop is the first part of the signal that comes in. And what would be perfect is to remove it around here. We can copy paste this. We could make a VI here which said remove it, but we won't. We're not so interested in the total size here. So what we're interested in this part and this part. So we'll copy this, put it here. So what we also need is we can have this indicator too, just for ease. And we'll call it additional signal to remove. Okay. And we like to have indicators on the left side, so it might seem a bit strange to have it this far away and overcross everything, but it's easier to view when you have every indicator on the right side and the inputs on the left side. The same as last time, we'll put the signal in here, and this will remove the amount we request with this one from the signal. And then we put this back in here. And put the waveform in here. And the output waveform should be this one. We just edit what we want. We could make a new waveform rather than edit the waveform we're using, but since all the metadata or the additional data connected to it is in the wire, it's better just to leave it be and only edit what we want to edit. So now we have found a way to remove the additional signal. So just add that here. So we'll just add a comment here. Removes more of the signal. This can help if the filter needs time to stabilize. And there you go. So this is this part. And we can just move it a little bit away from the other part so we can see the difference. And let's try this function out. We also need to map this one to an input. So let's do that. Just put it there and then move it so it's where the input is. Go back to our VI, filtering the signal, and make a controller, create controller. And there we go. So let's start it now. We see the same wave here, and just to show you what it does, I'll stop the auto scaling of the y-axis so that this is fixed. And now we see it stopped around the middle here, which is 5 seconds. It's probably less, but let's just write 5. It would remove the part of the signal which is for the filter to stabilize. And we just got this flat, clean signal now. We got half the signal length, but That doesn't matter because we can just increase it here. The filter takes the same amount to stabilize regardless of the length of the signal. So this works out fine. But 5 seconds is a lot of time, so let's try to minimize it with some fancy technique. So let's go back here again. A solution to this is something called padding. There's different ways to pad signals, but for this one, we'll try to do it in a sneaky way. So you saw that the signal uses 5 seconds to stabilize, or the filter uses 5 seconds to stabilize. So what we want is to kind of just make it stabilize and then remove it. We can do this by duplicating and reversing the signal, and I'll show you how. Into the array here, and we have one that rotates the array, but that's not the one we want. Reverse the array. Here you go. So we reverse the array, and then we get another array, build array one. And we'll take the reversed one in here, and remember to put it on concatenate because we still want the 1D array. And we combine these, and then we put this one into the filter instead. In this way, we now have the twice the amount of signal for the filter to work on, but it's the same frequencies, so we don't add anything to it. The only thing we need to do now is to just remove the extra part. So we'll just put this here. We can move this one a little bit down here. And we'll do that just by this same VI, so I'll just copy it in here. Boom. Put this in here, there. And to decide the size we want to remove, we'll just take the size of the array, which is here. Array size. Because then we just remove half of the array, which is exactly what we want to do. And this way, we will get less noise. The maximum we have is 180 beats per minute. Okay, so let's start again. Let's set this one to 0 now so we can see the whole signal. So as we see, we don't have the start anymore. We don't actually need the remove additional signal, but sometimes we can get this noise anyway. But as you see, without removing any part of the signal, we have a nice clean waveform. And it's still the exact same waveform because we just added the extra part to and use that to stabilize the filter, and then we removed it again after it had filtered. So we can just add that here. Padded the reverse of the signal, and then move the reverse of the signal. Sometimes this might be obvious, so this is a little bit bad commenting, so I'll just add another reason for it. Since the filter uses a few seconds to stabilize. There you go. Here you go. So we pad the signal with its own signal, just reverse. We put that through the filtering, and I filter it between 180 and 20 beats per second. Then we remove the padded signal, the extra signal with the stabilizing part in it, before we place it back into the waveform. And after that, we have the option to remove part of the signal. This might be unnecessary now, but I've noticed sometimes there can be parts of the signal you want to remove anyway, so that's why I added it. So here you see the range here is a lot higher too because filtering weakens the signal, but we also have a much smoother waveform. And that's it for this lesson. And in the next lesson, we will finish up the simple heart rate monitor.